We were talking about confidence intervals, and I want to try to separate two pieces of the story. One is, what is a confidence interval? What does it mean? What's this all about? And then the other is, how do you calculate it in particular cases? So the more important thing, I think, is to understand what they mean, because very often you're going to read some article that's going to say, the answer is this plus or minus that, and to understand what that plus or minus number actually means is the important thing, and then be able to compute it yourself. Well, there's software to do that. You can always look up how to do that, but the understanding is crucial. All right, so here is, we'll just play with the simulation a little bit. This is a box of numbered tickets. It's a 0-1 box. The tickets are numbered. There's 3 zeros and 3 ones. This is really loud for me. Is it possible? Is it okay if I... It now says mute, but you can still pick me up? It says mute and it's still loud. Wow. Okay. Is that better? You still... Why am I still so loud? There's no PA. This thing is all the way down, and I'm still echoing. There's mic controls. How about that?
Yeah.
That's maybe it. Okay.
I need you up
the wireless.
a bit.
Okay, need me up a little. All right. Great. Okay. Yeah, that's better. That's better. Okay, great. I'm turning the wrong volume control is the problem. It must have been the DVD player's volume control instead of my mic. Okay. So we have a 0-1 box, and there's 3 zeros and 3 ones, so the mean of the numbers in the box is a half. This vertical line is at that value, the mean of the box, a half. And what we're going to do is draw a random sample of size 3 from the box and calculate the sample mean, the mean of that sample of size 3, and then we're going to go up and down from that mean by 2 times a bound on the error, a bound on the SE. So what's the standard error of the sample mean? If I take a sample mean of a sample without replacement of size 3 from a population of size 6, what's the standard error of the sample mean? Okay, so it's SD of the box. It's divided by the square root of n. So we're talking sample mean, not sample sum. So we divide by the square root of n, and then we have the finite population correction f, which is square root of big N minus little n over big N minus 1. Okay, so the standard error of the sample mean is, I don't have the number written down here, but it's going to be the SD of the box, which is the square root of p times 1 minus p, right? Times, divided by the square root of n is 3, and then times the finite population correction, which is going to be the square root of 6 minus 3 over 6 minus 1, so square root of 3/5. And what I'm going to do is I'm going to take an interval, I'm going to center it at whatever value the sample mean happens to be, and go up and down from that by twice, not the actual standard error, because we're going to pretend we don't know what's in the box, but a bound on the standard error. And the way we get a bound on the standard error for a 0-1 box is to pretend that there's 50% zeros and 50% ones in the box. That's the worst case for the standard error. That gives the standard deviation of the box as large as possible, namely a half. And so the bound on the standard error is, instead of using the square root of p times 1 minus p, we use a half. All right, so we're going to do that. We take a sample and go up and down. So this time the sample mean turned out to be this black dot, and we're going up and down from the sample mean by this number, twice the upper bound on the SE based on pretending that there's 50% zeros and 50% ones. So this interval turned out to include the population percentage, 50%. It didn't have to. If we got a different random sample, it might not have. And let's just do this. We'll do this a few times. Okay, so we're seeing that sometimes we get, so the intervals that are red are the intervals that don't include the truth. The intervals that are green are the intervals that do include the truth. When the interval includes the truth, it's said to cover. It covers the true parameter value. The other ones don't cover. And if you look at this, you know, most of them cover, some of them don't. Okay, in this particular case, we've seen that 83.3% of what we've got so far cover. Right? So we could do this a bunch of times. We could do this 1,000 times. And if we do this over and over again, this is going to give us the percentage that cover would be an estimate of the probability that this procedure gives you an interval that covers. So this is the empirical fraction of the time that the interval covers, but there's some probability that it covers, some theoretical percentage of the time that it ought to cover if you did it forever, if you kept going and going and going. All right, so these intervals that start at the sample mean and go up and down by twice the bound on the standard error cover a lot of the time. Right? How could we know that they're bound to do that? That's likely to happen. All right. Now, I showed last time using Chebyshev's inequality that what we know is that the population mean, the difference between the sample mean and the population mean is unlikely to be a large multiple of the standard error of the population mean. Chebyshev's inequality says the chance that that multiple is bigger than 2 is no bigger than 1 over 2 squared, 1 over 2 squared, so a quarter. So the chance that an interval that goes up and down by twice a bound on the standard error doesn't include the truth is at most a quarter. And in fact, here we're seeing it's more like 10%. It's not 25%, it's even less than that. So an interval that goes up and down by 2 times the bound of the standard error has at least a 75% chance of including the truth. And in fact, an even larger chance than that. Now, here we're able to see that which intervals cover and which intervals don't. But the situations where you're going to use a confidence interval are not where you already know what the truth is. It's going to be situations where you don't know what the truth is. So here, we're going to hide the box, and we're going to take a sample of size 1, okay? And the sample mean turned out to be right around 1, and we went up and down from the sample mean by some multiple of the standard error. Did we include the truth or not? We don't know because we don't know what was in the box, right? Okay, so in the general case, we're going to take some particular random sample, we're going to compute some particular interval. That interval either will or won't include the true value of the parameter, and we simply won't know, right? There's no probability left after you take the random sample. The numbers are fixed, right? There is some list of numbers in that box. The average of that list either is in this range or it isn't in that range. We don't know, okay? But there's no probability left. This either does include the truth or it doesn't include the truth. What do we know about the procedure? What are confidence intervals about? Well, what we know is the way we did this has a very big probability of giving us an interval that includes the truth. The procedure has a chance of at least 75% of giving us an interval that includes the truth. In any particular case, we won't know whether it includes the truth or not when we're using it because we won't know what's in the box. But most of the time, it's going to give us an interval that includes the truth. Some of the time, it'll give us an interval that doesn't. Is that clear? Make sense to everybody? Okay. So here I can reveal what's in the box. And it turned out that the mean of the numbers in the box was 0.7, 70%. And this interval, in fact, covered. But it didn't have to, right? There's some small chance that it wouldn't. Okay. So we can do this trick of finding an upper bound on the standard error of the population percentage, but there isn't a corresponding trick for getting an upper bound on the standard error of a general population mean. If you don't have a 0-1 box, the standard deviation of the box could be arbitrarily large. If you have a 0-1 box, the standard deviation of the box can't be bigger than a half. Right? So, moreover, even if you have a 0-1 box, unless the percentage of ones in the box is 50%, the standard deviation of the box is going to be less than a half. And this procedure we're talking about is very, very conservative for two reasons. One is a half is an upper bound on the SD of the box, and if the box has mostly zeros or mostly ones, a half is going to be way too big. And secondly, Chebyshev's inequality is an inequality, right? It's true for any probability distribution, and it has slack is sort of the technical word. When we're talking about drawing ones out of a zero, we're talking about drawing tickets out of a 0-1 box. The distribution of the number of ones you get in the sample, if you draw the sample without replacement, is hypergeometric, right? It turns out that Chebyshev's inequality isn't sharp for hypergeometric distributions. It gets strictly less than, not less than or equal to, for hypergeometric. So there's slack there, but the slack in both directions acts to make it conservative. So the chance that the interval includes the truth is at least as big as it's at least 1 minus 1 over k squared. Okay, rather than, okay, so we get something conservative. But now if we're willing to do something approximate, which would make sense if we have a large sample size so we can learn something about the SD of the box from the SD of the sample, then we can end up getting a shorter interval, but we're no longer conservative, we're approximate. So we don't know that the chance that the interval includes the truth is at least 90% or 75% or whatever the number is. We know that it's roughly that, and could be more, could be less. The larger the sample size is, the more, the closer to 90% or 75% or whatever the target is, the number's likely to be. Before we do that, I want to make sure to hit this point, which is when you look at a confidence interval for the population percentage, the confidence interval you get might, in the case we just did with the 70% population value, our confidence interval, if you look at it, went from a little below 0.5 to a little over 1.5. Okay? We know that the population percentage can't be bigger than 1, right? It's got to be between 0 and 1. Okay? If we truncated the interval at 1 and just ignored this, so we made the interval go from a little below 0.5 to 1 and stopped there, we wouldn't lose any coverage probability. We wouldn't lose any confidence because it's impossible for the truth to be out here. So ruling it out and just saying, okay, I'm going to stop the interval there doesn't cost us anything. It gains precision at no cost in probability, no cost in coverage. So typically, if you have a restricted parameter whose values have to be in some range, then you can always take your confidence interval and truncate it so that it doesn't go beyond that range. It doesn't compromise the confidence level, doesn't compromise the coverage probability. So in particular, if we're talking about a confidence interval for population percentage, there's never any reason for the lower endpoint to be below 0 or for the upper endpoint to be above 1. You can always cut it off. All right. So now we know that let's pretend, we're going to pretend for the rest of the chapter that we're drawing our random sample with replacement. So it's not a simple random sample, it's a random sample with replacement, or that the sample size is much smaller than the population size so that we can treat it as if it's drawn with replacement. The elements of the sample are almost independent. Okay? Now, what do we know? If we were drawing from a 0-1 box and we were drawing with replacement, then the number of ones we get in the sample has a binomial distribution, right? This ring a bell for everybody? Number of ones in independent draws from a 0-1 box, fixed number of draws, little n, has a binomial distribution. We know that the normal approximation of the binomial distribution gets pretty good provided p isn't too close to 0 or 100% and n is reasonably large, right? Typically, we know even more generally that the normal approximation to the sample mean or the sample sum of draws with replacement from a box of numbered tickets gets better and better as the number of draws increases, right? So if instead of using Chebyshev's inequality to get a bound on the probability that the sample percentage is very far away from the population percentage, we could use the normal approximation to get an approximation for the probability that the difference between the sample percentage and the population percentage is very big. Right? So that's what we're going to do now. I'm going to close the door just because. Okay, so Chebyshev's inequality says the chance that a random variable differs from its expected value by more than k standard errors is at most 1 over k squared. And if we use k equal 2, that says the chance that a random variable differs from its expected value by more than 2 standard errors is no more than 1 over 2 squared, 1 quarter, right? So there's a 75% chance that the random variable is within 2 standard errors of its expected value. The expected value of the sample mean is the population mean. Now the question is, what can we say about if we want to use the normal approximation instead? Well, the normal approximation says that the area under the normal curve between minus 1.15 and plus 1.15 is 75%. So by if the normal approximation holds, then the chance that a random variable that is approximate, that for which the normal approximation is good, differs from its expected value by more than 1.15 standard errors ought to be about 75%, ought to be about 25%. The chance that it's within 1.15 standard errors of its expected value ought to be about 75%. Is this okay? So if we look at an interval that starts at the population percentage less the 1.15 times the standard error of the population of the sample percentage. So this is the sample percentage for little n draws with replacement, right? So that's the SD of the box. That's square root of n. Okay, and then we go from the expected value up by 1.15 standard errors. Then the sample percentage has about a 75% chance of being in that interval. So we can turn this around and say, okay, whenever the sample percentage is in that interval, so here's the population percentage, here's this interval, so that's p, this is p minus 1.15 times square root of p times 1 minus p over square root of n. And this is p plus 1.15 root p 1 minus p over root n. Okay, so the sample percentage, which we've been denoting phi, it's random. Sometimes it's going to be in here, sometimes it's going to be out there, right? If it ends up being in, so if the normal approximation is good, then the sample percentage is going to be in this range about 75% of the time. Okay? When it's in that range, if I took an interval of this width, I should really redraw this so that I can use the eraser as a measuring stick. All right, so let's say that this and this are these values plus or minus 1.15 times the standard error. Okay, so what happens if the truth is, if the estimate ends up being here, and I go there minus this distance, there plus this distance, that range, oh, I'm sorry, I did this. Let's try again. I'm going to make the whole eraser be 1.15. That'll be easier. Okay, so this is the interval from the population mean minus 1.15 standard errors to the population mean plus 1.15 standard errors. Okay? And the claim is that if the normal approximation is good, then the chance that the sample percentage ends up in that interval is about 75%. Suppose that the sample percentage, we're in one of those 75% of cases. The sample percentage ends up being here. So if I start there and I go down by this, up by this much and down by this much, that interval to here is going to include the truth. That interval is going to cover. Okay? If it happens that the sample percentage phi ends up being out here, then an interval that goes up by this much and down by this much isn't going to cover. Right? That missed the truth. Okay? Whenever the sample percentage ends up being in this range, then an interval that's centered at the sample percentage and goes down by one eraser and up by one eraser is going to include the truth. right? Includes the truth. Okay. So because there's a 75% chance, approximately, that the sample percentage is within one eraser of the truth, there's a 75% chance that if you take the sample value and go up and down by one eraser, that's going to include the truth. It's like just turning the distance. If it's within this distance, it's within this distance. Okay. So, all right. Now, yes?
Is the 1.15 just happen to pick that number?
That was to get 75%.
Okay. But
okay.
It will change.
If you wanted to get 90%, it would be a different number. So like one of the things we know is if you go up and down by one standard error, that gives you about 68%. Up and down by two standard errors gives you about 95%. Up and down by three standard errors gives you 99.7%. Okay, so this is the normal curve numbers that we're committing to memory, or you know, for odd numbers we'll figure out what the... Okay. Okay, so if we knew the standard error, we could figure out what 1.15 standard errors was, and we could take an interval that's centered at the sample percentage and go up and down by 1.15 standard errors, and we would know that that interval has a confidence level associated with it of 75%, approximately. The problem is that we still don't know the standard error, right? Just like before, we don't know what fraction of zeros and ones are in the box, or we wouldn't be estimating it, right? If we knew the answer, we know the answer. So in order to know what we were doing before was we were saying, okay, I don't know what this number is, but I know that this number is no bigger than a half. And so if I plug a half in here, I've got a conservative answer. Right? Now, we're going to do something different, which is we're going to say, we're going to pretend, in order for the normal approximation to be good, for it to make sense to use this curve, little n has to be fairly large. The sample size has to be fairly large for the normal approximation to be good. Well, if the sample size is pretty large, then the sample percentage phi ought to be reasonably close to the population percentage p, in which case, if I use the bootstrap estimate of the standard error by plugging in phi, my estimated value of p, in both places, then that ought to be a reasonably good estimate of the SD of the box. Okay, and so to do an approximate confidence interval based on the normal approximation, we're going to do that. It's going to make sense if n is relatively large. We have a relatively large sample, so the normal approximation is good, and so that the bootstrap estimate of the standard error is likely to be a pretty good estimate of the true standard error. And so if we plug those numbers in, that leads to doing the following. We would take the sample percentage minus 1.15 times the sample standard deviation divided by the square root of n. That will be the lower end point of our confidence interval. The upper end point is the sample percentage plus 1.15 times the sample standard deviation divided by the square root of n. Right? So we're using the sample standard deviation to estimate the SD of the box. And then the SD of the box divided by the square root of n is the estimated standard error of the sample percentage, because we're drawing with replacement. So we don't need to worry about the finite population correction. All right, so there's an interval. This interval is random now in a couple of different ways. So first of all, the center of this interval is phi, right? It goes up and down from phi by the same amount. It goes up and down from the sample percentage by the same amount. So the middle is random. Where it happens to be centered is random. But it also goes up and down by an amount that depends on s. And s is random as well, right? S is the sample standard deviation. That depends on what sample you get. So the midpoint of the interval is random and the length of the interval is random. Both of these things are random. They're both going to contribute to the probability that the interval includes the truth. So far, are we all together? Any questions? All right. Okay, so here is, again, this box has 40% ones. 2 out of 5 of the numbers in the box are 1. The rest are 0. And we're looking at a situation with a larger sample size where the normal approximation starts to make sense. Right? Wouldn't want to use the normal approximation if our sample size was 3. It would not be a very good approximation. Sorry?
What else makes the normal approximation good?
Large number of draws, and if the true proportion of ones in the box is close to 50%. If the proportion of ones in the box gets too close to 0 or 1, then the distribution is really skewed and the normal approximation isn't going to be very good. However, we're using this in situations where we don't know the fraction of ones in the box, right? So, well, if you drew a sample of size 30 and you got almost no ones or got almost no zeros, then that would tell you you should be pretty confident, informally confident, not confidence level confident, but informally confident that the distribution of the numbers in the box is pretty skewed, and so the normal approximation is probably not going to be very good. All right. So, so let's look at this procedure. So now what we're doing is, again, we're drawing a sample of size 30. We're going to take one sample. We're going to go up and down from the sample mean by 1.15 times the estimated standard error. So the estimated standard error is s divided by the square root of n. All right, so if we do that, okay, that time we got an interval that didn't include the truth. Okay. That time we missed as well. There we hit. Missed. Okay, so what we should expect is that what? What fraction do we think we'll actually cover? Okay, so if we kept doing this, if the normal approximation were good, and we did this 1,000 times, let's go ahead and do this 1,000 times. If the normal approximation were good and we did this 1,000 times, then what should we get, roughly, over here? Should be about 75%, right? It's a little less than 75% for two reasons. One is the normal approximation isn't perfect, and the other is that we're not really taking into account the fact that we're estimating the SD of the box using S. We would want to inflate things a little bit because S is only an estimate of the SD of the box. Okay. If we increase the sample size from 30 to, say, 100, then what should happen? Or you think we're going to get further from 75%, closer to 75%? Okay. With a sample size of 100, two things are going to happen. The normal approximation is going to be better, and S is going to be a better estimate of the SD of the box. Okay, so this should give us something much closer to 75%. Okay, gave us 73%. If we make this 300, all right, now we're getting very close to 75%. Okay, so does this make sense? As the sample size is increasing, we're getting two things acting in our favor. One is the normal approximation to the distribution of the sample percentage is getting better. And secondly, the sample standard deviation S is becoming a better estimate of the SD of the box. Okay. All right, so here we have the contents of the box hidden. We're back in the situation before. We take a particular sample. There is some real list of numbers in the box. Those numbers have some mean. We don't know what that is. Here we got an interval that went from a little over 2.3 to about 3.2. That was the sample mean. We went up and down by 1.15 times the sample standard deviation. So by the way, this is not a 0-1 box anymore, is it? No. Okay. So there's some true list of numbers. It has some mean. This interval either includes the mean or it doesn't include the mean. We don't know which, but the probability is all gone. We've taken the sample. We have some number that's just either true or false that the interval contains. Okay, so if we reveal what was in there, it turned out that that list of numbers, the mean of that list of numbers was a little under 2.5, and the interval, in fact, included the truth. All right, well, this gets us to the next place in the discussion, which is what we just did for estimating the mean of a 0-1 box, making a confidence interval that's approximate using the normal approximation and using the sample standard deviation S to estimate the SD of the box. That didn't rely on it being a 0-1 box, right? in fact, we could do it with any box of numbers, and that's what this just did. We just took the sample mean and went up and down by a multiple of the estimated standard error. We picked the multiple that would be appropriate to get 75% coverage if the normal approximation is good. And we estimated the standard error by estimating the standard deviation of the numbers in the box using the sample standard deviations. With the sample standard deviation, which has the 1 over n minus 1 before, divided by 1 over n minus 1 before taking the square root rather than dividing by n. That was our estimate of the SD of the box. And then that divided by the square root of n is the estimated standard error of the sample mean, whether it's a 0, 1 box or not. And then by going up and down by 1.15 estimated standard errors, we get an interval that has approximately 75% coverage probability. Now, if the numbers in the box were really skewed, then the normal approximation to the distribution of their sample mean wouldn't be very good. And the chance that the resulting interval would include the truth could be very different from 75%. Okay? In this case, the numbers aren't, I mean, I don't know what the statistics are for the numbers in the box. There are a few big numbers. There's some, yeah, it looks like it's actually skewed to the right, if anything. But anyway, okay. For a sample size that is large enough, the normal approximation is still going to be good no matter what you started with in the box. But how big is large enough depends on what's in the box. And we don't know what's in the box. So we're always in this sort of catch-22 situation when we're using the normal approximation to try to make an approximate confidence interval for a population mean. You would know if the normal approximation was good if you knew what was in the box. But if you knew what was in the box, you wouldn't be using the normal approximation in the first place. You'd know the answer. Right. Yes? Mm-hmm. We are taking the sample standard deviation of the sample that we draw. So we drew a sample of size 250 with replacement from this box, and so there was 250 numbers. Call them x1, x2, on up to x250. And the center of the interval here, this is 2.77 or something like that, is the sample mean, m, which is 1 over 250 times the sum from j equals 1 to 250 of the xj's. Right? That's the sample mean. And then S is equal to the square root of x1 minus m squared plus x2 minus m squared plus x250 minus m squared divided by 249. Okay, so this is how we're estimating the SD of the box, okay? And then we're taking that divided by the square root of 250 as our estimated standard error. And then we're making our interval 1.15 times the estimated standard error. Other questions about this right now? Okay. All right. Let's look at the first exercise here. I want to know what fraction of UC Berkeley undergrads commute to school from their parents' homes. So I send out emails until 100 students have responded, and 3 of the people who responded were commuters. So what's an approximate 95% confidence interval for the fraction of UC Berkeley undergraduates who commute? Yeah, so this is the answer is there isn't one from these data, right? This is a trick. I mean, I don't know if it's a trick question, but we have no idea how many people were asked until we got 100 people who responded, right? We have no idea how large, what the non-response is in this survey, right? Okay. This is not a random sample of 100 students. It wasn't 100 students picked at random. It started off as a sample of convenience. We just sent email out to people. And then having started with the sample of convenience, we had an unknown non-response rate. We don't know how many people were contacted in order to get 100 to respond, right? So you can't get a confidence interval unless you start with a random sample. This is not a random sample, no confidence interval. Okay? Sorry? You don't. Well, I mean, I don't think that there's. I think everything is going to get counted as wrong. I mean, oh, answer 0. Okay. Oh, okay. Yeah. Okay, so what can you say if you want to get a confidence interval for the fraction who commute? What interval can you get? 0 to 100%. Exactly. So that's all you can do. Right? The data are irrelevant. Actually, you know a little bit more, right? You know that there's at least 97 students who don't commute and at least 3 who do commute. And so you could, if you knew how many students there were in all, you could sort of subtract those off and do a little bit better than 0 to 100%. But you don't have a random sample. Okay. All right. So let's look at this one. I want to know what fraction of homes in Alameda County have assessed values of $700,000 or more. I take a simple random sample of size 400. The sample percentage that are assessed at 700,000 or more is 6%. And I'm asking for an approximate 92% confidence interval. Okay, so first of all, 92% is a weird confidence level. The only reason for having it here is to get you guys familiar with using the normal curve to figure out what multiple of the standard error you ought to use. The common confidence levels that you see in practice are 68%, 90%, 95%, 99%. Those are pretty much all anybody actually uses, but they're arbitrary. There is no reason to take a particular confidence level over another confidence level. It just affects how you interpret the result. The important thing is that you report what the confidence level is for what you did so that people can make sense of it. And if you find somebody has reported a confidence interval of, the confidence interval from -2 to -1.2, you have no idea what that means unless they tell you what the confidence level is that it goes with the confidence interval. Okay, so you need to know the confidence level. All right, so what do we got? We've got, what is the sample percentage? So we've got a simple random sample here, right? This is good. 400, how many homes are there in Alameda County? A bunch, right? 400 is a very small fraction of the number of homes there are in Alameda County. So the finite population correction is going to be effectively 1. We can treat this simple random sample as if it were a random sample with replacement. Moreover, in general, if you ignore the finite population correction, if you pretend that f equals 1, what's that going to do to the length of your confidence interval? It'll make it longer, right? If f is really less than 1, but you pretend it's 1, then you're saying the standard error is bigger than it actually is, and as a result, you get a longer interval. What's that going to do to your confidence level? It should make your confidence level higher, right? Longer the interval, bigger chance that the interval is going to contain the truth. All of the things being equal. Okay, so ignoring the finite population correction just makes things more conservative. Here we're asking for something approximate, not conservative, but let's carry forward. Okay, so we're going to take f to be essentially 1 because 400 is a very small fraction of the total number of homes. And the sample percentage is 6%. Now, how far up and down from 6% should I go to get an approximate 92% confidence interval? So I need to know, first of all, what's my estimate of the standard error is what? Okay, so it's going to be approximately 0.06 times 1 minus 0.06 divided by the square root of 400.
Oh, they're both. Oh, because it's simple.
Okay, right. So that we're estimating we're estimating the SD of the box by pretending that the sample percentage is the population percentage. Okay, this is giving us this is really S star. And then we are dividing by the square root of the sample size because we're treating this, and we're not using F because 400 is a tiny fraction of the total number of homes. Okay, square root of 400 is pretty much 20, I think. This I don't think I can do in my head. Let's bring Google to the rescue. Square root of 0.06 times 0.94. Okay, so the estimate of the SD of the box is 0.237. We're going to divide that by 20. Right? That's now our estimated standard error of the sample percentage, but we need to know how many multiples of that to go up and down from the sample percentage in order to construct our confidence interval. And for that, we need to look at the normal curve. So if we want to end up with approximately 92% coverage, first of all, what am I going to need to do to these numbers? I'm going to need to make this wider, right? To increase the area from 75% to 92%. Okay, I know that 95% is about 1.96. So that's a little too much. So let's try minus 1.9 to 1.9 for grins and just see what that does. Okay, that gave us, that's still a little bit too much. Okay, looks like 1.75 kind of does the trick, yeah? All right, so if we take this, 1.75 times that, that gives us 2.08%, right? 0.02078 is 2.08% for the sake of argument. So what is our confidence interval going to do? We're going to start at 6% and go down. So our lower end point is going to be 0.06 minus 0.02078. And our upper end point is going to be 0.06 plus 0.02078, right? Okay, 0.02078. So let's go back to where the endpoints. The endpoints. Yeah, exactly. So the lower endpoint. Oops. So I'm going to put the math in here. 0.06 minus. So remember, don't do this on the homework because the server will not grade it correctly, but you can do it in the chapter because this will do the math for you. Question?
Yeah. Why do you multiply 1.75 by the estimation? I feel like you should divide by how many standard errors are from the standard of classification.
Okay, so what is the normal curve, the area under the normal curve telling us? It's saying that if something follows, if the normal curve is a good approximation of the probability histogram, then the chance that a random variable, once you put it in standard units, is between minus 1.75 and plus 1.75 is about 92%.
It's 1.75 standard units down, 1.75 standard units up.
Right. Yeah. Sort of once you put it into standard units, the chance that it's between minus 1.75 and plus 1.75 is about 92%. Okay. So how do you get it to standard units? You subtract the expected value and you divide by the standard error. So another way of saying that is the chance is if the normal curve is a good approximation, then the chance that the random variable is between 1.75 standard errors below its expected value and 1.75 standard errors above its expected value is about 92%. Okay, so what was this? 0.02078 and 0.06 plus 0.02078. Okay, all right. It's always the moment of truth when I put the answer in the box. It's like, okay. All right. If the sample size had been 4 instead of 400, would this have been a reasonable thing to do, this procedure? No, because the normal approximation would not have been very good, right? And moreover, the sample standard deviation would not have been a very reliable estimate of the standard deviation of the box with a sample of only size 4. So the approximation would have been bad for 2 reasons. It would not have been a good approximate confidence interval. In that situation, we might have used the conservative confidence interval based on Chebyshev's inequality and the upper bound for the SD of the box of of a half. Did that make sense? Yeah.
But why is this even good? 'Cause it's only 400 out of like all of the help.
Right. Okay. So how do you get a good answer? Why is this range so?
Yeah. Why is that? I mean, I know it's a lot better than 4, but it's still not very good.
Well, okay. So I mean, the answer is that it's good to about plus or minus 2%. That at 90% confidence, at 92% confidence, you know, the answer is 0.06 plus or minus 0.02. If you wanted to know it, to pin it down more accurately, you would need a larger sample. And if you had a larger sample, these plus or minus numbers would shrink. So it's an unbiased estimate. The 0.06 is unbiased because it's a simple random sample. The question is, so you know, if we took samples of size 400 over and over and over again, then sometimes the answer would be below 0.06. Sorry, sometimes the answer would be below the truth, whatever the truth happens to be. We don't know what it is, right? Sometimes it would be below that. Sometimes it would be above that. But on average, it would balance at the truth. Okay, question is, how much above that, how much below it does it tend to be? Well, on average, it tends to be off by about 1 standard error. And on average, it tends to be, you know, it will tend to be within, for a sample of size 400, it will tend to be within the number that we calculated here from the sample of the truth about 92% of the time. Okay? Now, for a different sample, the 0.06 would change, which changes the midpoint of the interval, because this is 0.06 plus or minus something. And for a different sample, if we got a value other than 0.06, that would also change our estimated standard error, and that would then thereby change the amount by which we go up and down. For example, if our sample percentage had been 50%, then our estimated standard deviation of the box, instead of being this number, would have been a half, right? Because it would have been the square root of a half times a half, which is a half. Okay? So we would have gotten a longer interval. Yep. Yes.
When you change these inputs, then your percentage of confidence interval will also change?
So the procedure we're using here, we specified ahead of time that we're looking for a 92% confidence interval, which again is an odd number to pick, but that's what we're doing to just go through the whole calculation. So our procedure is draw the sample, compute the estimated standard error, and go up and down from the sample percentage by 1.75 estimated standard errors. Okay? That procedure is going to give us a different interval for different samples. Right? Different samples are going to end up having different midpoints, different endpoints. What we can say is if that's the rule that we're going to use, the chance that we end up getting an interval that includes the truth is about 92%. Okay? For some samples, that interval is going to be longer than this. For some samples, that interval is going to be shorter than this because that procedure produces an interval whose length depends on the sample. So some of the times the samples are going to give a long interval, sometimes they're going to give a short interval. If the sample percentage happened to be 0, this would give us an interval of length 0, which would clearly be silly because it would say that we sort of are absolutely confident that there are no homes in Alameda County that are assessed over $700,000. But at any rate, the closer to 0 or 100% the sample percentage is, the closer to 0 the estimated standard error is, the smaller the estimated standard error is. Right? So the estimated standard error is going to depend on the sample. The sample mean depends on the sample. So we get something where the length and the midpoint depend on the sample. But the procedure that says go up and down from the sample mean by 1.75 estimated standard errors, that procedure has probability roughly 92% of giving you an interval that includes the truth. In this particular case, we wouldn't know whether this interval in fact includes the truth. The interval is random. It might include the truth. Sorry, it's the result of something random. It might include the truth. It might not. At this point, it's either true or false that it includes the truth. There's no probability left. Right? Okay. Before you take the sample, there's probability. After you take the sample, it just includes the truth or it doesn't. Deal's done. Yes?
Okay, so kind of just like, this is saying that there's a 92% chance that, or confidence.
92% confidence, yep.
That there are something like 4 to 8% of homes in Alameda or 7,000 or more.
Yep.
Oh, okay.
Okay, that's exactly it. That this is saying that we have 92% confidence that the percentage of homes that are valued at $700,000 or more by the tax assessor is between about 8.07%, sorry, between about whatever that is, 3.93% and 8.07%. Yeah.
So if we keep the sample size in our sample constant, then the endpoints and the confidence interval is indirectly related, so that if we smaller the endpoints, then the percentage of the confidence interval will increase, right?
If instead of going up and down, so we just figured to go up and down by 1.75 standard errors to get roughly 92%. If we went up and down instead of 1.75 by say 1.9, we would get a higher confidence level. We went by 1.9 standard errors. Now, there's this funny, in this particular case, because we're talking about a sample percentage, there is this funny indirect relationship between the center of the interval and the length of the interval. Because the closer the center of the interval is to 0, that means that the sample percentage was smaller. If the sample percentage was smaller, then the estimate of the SD of the box is also going to be smaller. And so the length of the interval is going to be shorter. If the sample percentage were really close to 1, then again, our estimate of the SD of the box would be really small and the interval would be shorter. So the interval that we get by this procedure when we're looking at a sample percentage is going to be longest when the sample percentage happens to be close to 50%. And it's going to be shorter if the sample percentage ends up being close to 0 or close to 100% because our estimate of the SD of the box gets smaller. In general, if we're talking not about 0, 1 boxes, but about boxes with an arbitrary list of numbers, then there isn't that sort of indirect relationship between what's the center and what's the length, because the scatter is a different thing from the mean. So far, so good, more or less. Okay, let's look at this one. Random sample with replacement, size 10, drawn from a box of tickets. It's a 0, 1 box. 2 of the 10 tickets in the sample are labeled 1. The other 8 are labeled 0. What's the sample percentage? Does anyone disagree with that? Okay, sample percentage is 2 out of 10, right? 0.2, 20%. Is the sample size large enough to justify treating S as a good estimate of SD to the box? Sample size 10. It's small. 10 is just small. I mean, we're going to want numbers like 50, 30, 50, 100 before starting to treat S as a very reliable estimate of the SD of the box. Okay. All right. So this is not large enough to treat S as a good estimate of the SD of the box, nor to use a confidence interval based on the normal approximation, right? That should say normal approximation, not normal distribution. I need to fix that. Does that make sense? That binomial n equals 10, the normal approximation isn't going to be great, even if you have 50% ones in the box. What is the standard error of the sample percentage? We don't know what's in the box, right? We do know that it's not all zeros and it's not all ones. So there is actually a correct answer to this that we marked incorrect. Because we do know that it's at least 0, but that's not what I'm looking for. What are we trying to do here? Okay, so you're suggesting looking at the square root of 0.2 times 1 minus 0.2 over the square root of 10. Okay, so is this going to be, is this equal to, is this approximately equal to, is this, what is this? Okay, so the conservative would say that it's at most the square root of a half times 1 minus a half over the square root of 10, which is a half over the square root of 10, right? Okay, this is not going to be a very good estimate because the sample size is so small that 0.2 isn't going to be a good estimate of the fraction of ones in the box. 0.2 here is the fraction of ones in the sample, not the fraction of ones in the box, right? So this is an approximation, but it's not likely to be a very good approximation. Here we do know that this upper bound is true. Yes? The upper bound only works for 0, 1 box, and that's what we've got here. It's the, okay. Okay, so we know that this is at most, and what this ought to be is something like, I don't wonder if I've got square roots or not, I don't even remember. 0.5 divided by, no, it's not taking the square root correctly. We need to actually, um, 3.1622. Okay. All right, so now we're asking, so this number 92% appears in both places, but that was an approximate 92%. Here we're looking for a conservative 92%. Right? To make it conservative, we only know how to do conservative if it's a 0, 1 box, right? If it's a general box of tickets, there's no conservative answer based on the kind of stuff that we're doing. How do I figure out how many? So I'm going to, instead of using an estimated standard error, I'm going to use the upper bound on the standard error, right? This worst case analysis. And how much do I need to go up and down from the sample percentage? 1.75 would be for the normal approximation. We want to do something conservative. So I want to find the number k such that 1 minus 1 over k squared is equal to 0.92. Right? Okay, so if I go up and down, so the chance that I'm within k standard errors of the expected value is going to be at least 92%. Okay? So how do we do this? Yeah? Okay. So 1 divided by square root of 0.08 is 3.536, let's call it. So I want to go 3.53, well, let's just leave that there, times what? It needs to be this many upper bounds on, this many times the upper bound on the standard error, which the upper bound on the standard error was 0.5 divided by the square root of 10. Yes? Am I doing this right? Might want to put in some parentheses just to make it clear what's in the numerator and what's in the denominator. Okay, and so this is now, what have I got? I've got k is that 1 over square root of 0.08, right? That's the multiple k that Chebyshev's inequality is giving me, times the upper bound on the SD of the box, 0.5, divided by the square root of the sample size, square root of n. And that's the amount by which I need to go up and down from the sample mean, the sample percentage in this case. What is the sample percentage? Right? 2 out of 10. Okay. So if I take 0.2 minus 0.559, I get minus 0.359, right? Which is a negative number. Sample percentage has to be between 0 and 1. Sorry, the population percentage has to be between 0 and 1. So does the sample percentage, but we're talking about the population percentage. So I could either put in, minus 0.359, but if I program this correctly, then 0 ought to work also because it can't be any less than 0. Ooh, how about that? Okay. And then the upper bound is 0.2 plus 0.559, which would be 0.759. Okay. All right, so based on a sample that small, to get a conservative 92% confidence interval, we've covered almost the whole range of possible values from 0 to 100%. That size sample isn't telling us a whole lot, using this method anyway. Okay. Does the rhythm of this make sense? Does the calculation make sense? It's a good time to ask questions. That based on this sample, we have 92% confidence that the population percentage is between 0 and 75.9%. P, population percentage P.
And so that, P would be the number of zeros in the box?
The fraction of ones in the box.
Okay, it's always 1.
Yep.
I'm not sure if you can take this step, but what's the confidence interval, or I don't know, whatever, should be greater than 0.75?
The
What's the chance? Is it possible for it to be greater than 0.75?
right. It could be greater than 0.759. We're 92% confident we're at least 92% confident that it's between 0 and that it's not bigger than 0.759. No, and for a variety of reasons, but partly we're doing all these things that are conservative, right? We're making it wider and wider and wider and wider. And so my guess is that the true confidence level associated with this interval is probably 99 point something percent. And there's, okay. All right. We've already talked about this. Well, let's just do an example here. So we have a company that makes LED lighting, and they want to estimate the average lifetime of their bulbs. They take a simple random sample of 100 out of a manufacturing lot of 32,000. The mean lifetime of those bulbs is 101,000 hours, 101.48 thousand hours. The sample standard deviation is 3.57 thousand hours. And now we want an approximate 92% confidence interval for the average lifetime of bulbs in this manufacturing lot. Okay? So we're kind of stuck with an approximate. We can't do a conservative because this isn't a 0-1 box, right? The numbers in the box, there's 100 that we're getting 100 numbers that are, 101,000 hours, give or take, right? Okay, so what do? Is a sample of size 100 big enough for the normal approximation to be good? It's impossible to tell really because it depends on the distribution of the list of numbers in the box, but it's big enough to give some comfort. Okay, so it's a reasonable thing to do in this case. You're being invited to do it in this case, right? So we have a sample of size 100. Population size is 32,000. F is going to be very, very close to 1, right? Let's just write down what the endpoints are as expressions, and then we'll plug them in. All right, so in thousands of hours, the lower endpoint of the confidence interval is going to be 101.48 minus if we wanted to use F, we'd be doing what? Sampling without replacement. Okay, so it's the finite population correction. If we drew the random sample with replacement, F wouldn't be an issue. F isn't really going to be an issue here because 100 is so small compared to 32,000. It's going to be a fourth decimal place kind of difference here by the time we're done. Okay, and now we want times 3.57 divided by the square root of 100 times one more thing. What's missing? What's this? That's our estimate of the SE of the sample mean. Okay? And what we want to do is go below the sample mean by some multiple of the SE. Right? What multiple should we use? Yeah. 1.75. I think that actually above it went to 1.751 is a slightly more accurate result. Okay? And then, so this would be the lower endpoint of the interval, and the upper endpoint of the interval would be the same thing, but with a plus sign. Right? We'd go up from that by that much. So what have we got? 101.48 minus square root of 32,000 minus 100 divided by 31,999, close parenthesis. And that's going to be times 3.57 times 1.751 divided by 10. I'm just moving the 10 over to get rid of the ambiguity. So that looks like 100.856 thousand hours. Okay. And then the other would just be adding instead of subtracting. Yes? Okay. Does this make sense to people? All right. The next section, I don't want to belabor it too much, but I just want to point out the fact that this chapter so far has been about finding conservative confidence intervals for a population percentage and approximate confidence intervals for population percentage or population mean. But things that are like means aren't the only things you can find confidence intervals for. You can find confidence intervals for all kinds of things, like the population standard deviation or percentiles of a population. And this section of the chapter talks about a way to find a confidence interval for percentiles of a list of numbers based on a random sample from the list. So confidence intervals are a general notion. The idea is you want a procedure that produces an interval that depends on the sample. And what you want is that the way the procedure works is it has a big probability of giving you an interval that includes the truth. Right? The probability that it gives you an interval that includes the truth is the coverage probability. When you're done, we don't talk about probability anymore. We talk about confidence level. Because once you actually crunch the numbers, once you get the interval out, it either does or doesn't include the truth. There's no probability associated with it anymore. It's just does or doesn't. We talk about confidence level instead of coverage probability. So far, so good? Okay. We've got a little more than 5 minutes left. I think I want to just start briefly talking about the next set of ideas because I can vapor on about it a little bit. We talked about hypothesis testing without really using those words when we were talking about the let's make a deal problem. And was the chance of winning by switching a half or 2/3? We're trying to decide between two different states of the world. In one vision of the world, the chance of winning by switching is like drawing from a box that has one ticket labeled 0 and one ticket labeled 1, and winning is like getting the ticket labeled 1. In the other vision of the world, winning by switching is like drawing from a box that has 3 tickets, 2 tickets labeled 1, 1 ticket labeled 0, and drawing a ticket labeled 1 corresponds to winning. So this kind of trying to decide between two different hypotheses about the world, two different ways the world might work, two different things that might be going on, happens an awful lot. And it's the subject of this chapter, and I want to talk about some real-world examples of this sort of thing. So airport security, when you walk through the metal detector, what they're basically trying to decide is between two hypotheses. Either you are carrying a weapon or you're not carrying a weapon, right? And the system, any system for deciding between two hypotheses can make two different kinds of mistakes. In the example of the let's make a deal problem, it might have been that in reality we were drawing from box 1, but we erroneously conclude we're drawing from box 2. Or it could be that in reality we're drawing from box 2 and we erroneously conclude that we're drawing from box 1. Okay, so there's two kinds of mistakes that we can make. So in the metal detector story, there's two kinds of mistakes that it can make. You can get a false alarm. The alarm goes off and the person isn't actually carrying a weapon. They just have, lots of fillings or body piercings or something, right? Alternatively, somebody could be carrying a weapon but go through the metal detector and the metal detector doesn't go off. doesn't sound the alarm, right? So one kind of mistake, the two kinds of mistakes have different importances in this problem. Which is more serious? Yeah, letting somebody with a weapon go through, right? That's a more serious error here. But basically, you're stuck. There's always going to be two kinds of error in that situation. If you turn up the sensitivity of the metal detector to make sure that nobody can sneak through with even a sharp needle, then you're going to get a lot of false alarms, right? If you want to drive down the probability that you let somebody through with a weapon, you're going to drive up the probability that you have a false alarm. Does that make sense? Okay. Dental checkup. Dentist is basically trying to decide between whether you have one or more cavities or whether you don't have any cavities, right? And there's two kinds of mistakes they can make. Somebody can think you have a cavity when you really don't, or not notice a cavity that you actually have, right? Typically what happens in both of these situations is that there's a follow-up test, right? If you set off the metal detector in the airport, then they'll frisk you, or they'll go over you with a hand metal detector, something that's more accurate where they can localize the reason and understand better what's going on. If the dentist is probing your teeth and feels something that might be a soft spot, he or she might then have you get an x-ray, right, to follow up with something that's more sensitive to rule out the possibility of a false alarm, okay? All right, you want to test whether a headache remedy works. Two kinds of mistakes you can make. You could conclude that something that really has no effect at all has an effect, or you could fail to notice that a remedy that really is effective is effective. All right, so the kinds of errors so in all of these cases, there's a natural null hypothesis. So typically, we call the hypotheses the null and the alternative, and a type 1 error is to reject the null hypothesis when the null hypothesis is in fact true. So when you go through the metal detector, the null hypothesis is that you are not carrying a weapon. And a type 1 error occurs if the alarm goes off and you are indeed not carrying a weapon. It's a false alarm. It's a type 1 error. Okay? A type 2 error is to fail to reject the null hypothesis when the alternative hypothesis is in fact true. So a type 2 error in the metal detector case is you're carrying a weapon, you go through the metal detector does not go off. Okay? So you're not noticing that something is happening. The dental checkup, the null is that you don't have any cavities. A type 1 error is to conclude that you have a cavity when you really don't. Type 2 error is not to notice a cavity that you actually have, to miss the cavity. Okay, so type 1 error, sort of false alarm. Here, null hypothesis is that the remedy doesn't work. A type 1 error would be to conclude erroneously that the remedy works when in fact it doesn't. Type 2 error would be to fail to notice that it works when it does. Some more maybe relevant to everyday life examples these days. Search engine, when you run a query on Google or Yahoo or Bing or whatever, the search engine is basically is going through a catalog of documents that it's indexed, and trying to decide, based on what you typed into the search box, whether you are interested in this document or not interested in this document. And it tries to return to you the documents that it thinks you will be interested in and suppress the rest. Okay? Only give you those things that it thinks that you will find interesting. So the null hypothesis might be, for a given document, this document isn't interesting to the user. And to reject that null hypothesis is to conclude that it is interesting and show it to you, right? Return it as part of the search results. A type 1 error occurs if you get shown a document that you really didn't want to look at. And a type 2 error happens if there's a document that you would have liked to see that doesn't get returned as part of the search results. Okay, it doesn't get sent to you. So again, two kinds of errors that you can make in any particular case. All right, I'll let you guys go. Thanks for being here today. Office hours today, I remember, are a little bit late. I have a meeting, but I'll be there around 1:40 to 2:40.